This video looks at two methods for differentiation of inverse trigonometric functions. We're asked to differentiate y equals tan inverse x over the square root of 9 minus x squared. I'm going to show the first method using the tan inverse formula that's given in the log tables. This, however, turns out to be quite complicated and long-winded, so I'm going to show you an easier way in method 2. Here's the formula in the log tables. The formula is the rule though for tan inverse x over a. We don't have x over a, even though it looks a bit like this, but everything inside our brackets in the given y function is actually a function of x. There's an x in both parts of this. So we'd like to write all of what I've coloured in purple here as a fraction. So to do that, I'd write it as over 1. So we could write our fraction as x over the square root of 9 minus x squared over 1. So into the formula, a is going to be 1, and we're going to replace x with the x over the square root of 9 minus x squared. And then we will use the chain rule. So that's straightforward enough to do, although it's complex. So the plan is we're going to get the derivative of the outside and multiply it by the derivative of the inside. The easy bit is the derivative of the outside. So I'm going to sub into the formula 1 for a and x over the square root of 9 minus x squared for x. And I multiply that by the derivative of the inside, the purple part. Now notice that's a quotient, so I have to use the quotient rule. Now the purpose of the video is not really to show you this, so I'm going to quickly do this. If you want to take your time on it, you can. So it's going to be using the formula v times du dx minus u times dv dx all over v squared. However, the v squared itself is using the chain rule because it's the square root of 9 minus x squared. Be careful, the chain rule applies to this. And it's going to be all over v squared. Now, this is the solution, that's the answer. We want to tidy it up, however, because it's quite messy. So I'm going to be adding fractions, reducing fractions here. So again, I'm going to let this happen rather than discuss it. If you want to take your time and try to do it yourself, you could. So I'm going to neaten this up by adding fractions and reducing it. So multiplying above and below in the first fraction by 9 minus x squared. Makes that simpler. In the second fraction here, the numerator, I want to add these two fractions, so I'm going to multiply the first of these by the square root of 9 minus x squared above and below to give a common denominator as the square root of 9 minus x squared. And we see there is a cancellation here. 9 minus x squared goes into 9 minus x squared once. So I'm left with the following. Again, 9 goes into 9 once. So the final solution is 1 over the square root of 9 minus x squared. But it's quite complicated and long-winded to break down that original long-winded fraction to look like that. The second method, a way of doing this, is to understand that what I'm dealing with here actually is an angle. Tan inverse of a ratio is an angle. And I could imagine that angle, let me call it just theta or something to give it a name. I could draw a diagram of what that might look like. So I could draw a right angle triangle where we know what tan is. So let's call this angle here, one of the angles, theta. The opposite, which is x, over the adjacent, which would be the square root of 9 minus x squared, might describe that triangle. Now looking at this, if we knew the hypotenuse, it turns out the hypotenuse is a much simpler number. So using Pythagoras' theorem, the square here would be x squared. The square here would be 9 minus x squared. And the square here would be the sum of these. And when I add 9 minus x squared to x squared, I end up with 9. Which means that this side that we don't know the hypotenuse is actually a length of 3. So sine, which is opposite over hypotenuse, would be just x over 3. Which is much less complicated than tan. And if that's true, it follows that theta is equal to sine inverse x over 3. Now there's a rule in the log tables for finding the derivative of sine inverse, and it looks like this. It says if y equals sine inverse x over a, well then dy dx is equal to 1 over the square root of a squared plus x squared. So in this question, we can see that our x is just an x, and we can see that our a is 3. So our answer to dy dx is 1 over the square root of 3 squared, which is 9 plus x squared. This is the same solution as we got before. However, my headache has been reduced greatly.